Yeah, this is a course on many body theory. It's one that I've given quite a few times as a part of the CDT. That was apparently the last time I updated it, but I think I have updated it since then, but I just didn't change the date. I'm going to do it on my iPad, as I said. So unfortunately, I'm going to be doing this quite a lot as well. But I'll try to make eye contact with you occasionally. Let me go through what I'd like to do in the next well, 5 lectures is technically what I've got. So today I'm going to go through the formalism of second quantization, and this is probably something that's familiar to some of you. I'm guessing some of you are theorists, some of you might be experimentalists. So I'm starting pretty much at the beginning. I'll start pretty basic, and I'll introduce this formalism, which I think is useful to you because you'll undoubtedly encounter this. Then I'll move on to applying it to some simple examples that are actually quite useful, like Hartree-Fock theory and BCS theory. I'll then move on to talking about Green's functions and linear response, which is certainly going to be a part of any experimental theory that you might do, experimentally relevant theory. And then the last 2 lectures will look at Fermi liquid theory, applying the tools of second quantization to that, and then which is a weakly correlated system, and then a strongly correlated system at the end, which is the Mott insulators and Hubbard model, which you've already encountered in Sven's lectures, I would suspect. Okay, so there is some light reading you could do to supplement this course. I've got a selection of books here, which are all very useful. This book's not very well known, but it's actually a really nice introduction to many body quantum theory. The title's a bit weird. I'm not quite sure why they chose that title, but actually it's a book about many body quantum physics. This book is also really nice. Piers Coleman's book on Introduction to Many Body Physics. It's a massive book. It took him many years, I think about a decade, to write it. It's really nice book. So I've numbered the books, and you'll see various places in my slides where you can find more information about a given thing. I'll point to these books, and yeah, and Atland and Simon's book is also very nice. There's another book here on Feynman diagram techniques, which I'm not going to talk about much in this course, but if you wanted to know more about it, this is a really nice book for that as well. So yeah, so these are the kind of standard theoretical condensed matter textbooks. Fetter and Wallaker and Mahan are classic texts, but I don't use them too much here, but you might also find them useful. Okay, so a little bit of motivation. We're interested in many body physics, and the reason for that is because of collective effects. So there's this quote from Dirac that I quite like, which has a green part to it, which is nice. There's the fundamental laws necessary for treating a large part of physics. And I particularly like this: the whole of chemistry is completely known. So Dirac considered chemistry done. But there's a sting in the tail of his quote, which is the difficulty lies in the fact that the application of these laws to equations that are too complicated to solve. That's the many body problem. And obviously the founding fathers of quantum mechanics knew all about this right from the beginning. But what they perhaps didn't understand is the idea of emergence and collective behavior as we do now. And that's largely come about from the idea that a big conglomeration of particles often behaves very differently to few body problems with only 1 or 2 or 3 particles. So when you scale it up, you get what's called more is different. That's exactly the title of this famous paper by Anderson back in the 70s. And it's essentially telling us that we need new concepts to describe the emergent phenomenon that arises from many body systems. So there's hierarchies of different levels. Okay, so the nice thing about condensed matter physics is we actually have what you would consider to be a theory of everything. And essentially it's what's written down here. there's a paper about this as well, a rather nice one by Robert Laughlin in the Proceedings of the National Academies of Science back in 2000, where he explores this this concept of a theory of everything in condensed matter, and it contains all the things that you would normally think it could contain. It contains something to do with the electronic motion. It contains something to do with ions, so their motion. It contains the interaction between ions, and it contains the interaction between electrons themselves, and it contains the interaction between electrons and ions. And various parts of condensed matter spend a lot of time studying different bits of this theory. In particular, if you're interested in phonons, and then you would look at the ions and how they're coupled to each other. If you're interested in band structure, you're particularly interested in the potential that's created by the ions. And what we're going to spend a lot of time looking at is basically a lot of time looking at free electrons, and then some time looking at how we can handle electron-electron interactions. Okay, so we're going to spend a lot of time about how to reformulate this problem in order to allow us to add this to it. And this makes life very hard this term, and also exciting. Okay, good. So we're not going to do much about any of these things. We're going to treat those fairly on a fairly basic level. Assume that there's a crystal around, and so the other courses would have dealt with those. Nonetheless, on an electronic level, we know that quantum matter can exhibit a remarkable number of collective phenomenon, which you've already heard about in various other courses. So everything from magnetism, superfluidity, superconductivity, maybe even supersolidity, topological order, fractional quantum Hall effect, Bose-condensation. These are all remarkable collective phenomenon that only happen at the many-body level. And so we're going to touch upon a couple of these. So we'll touch upon superconductivity because we'll deal with the BCS theory, but we won't touch upon many of the others in this course. All right. So what kind of journey will we be taking? I've listed here a bunch of topics, and I've listed them in terms of weak to strong correlations, and that's a slightly ambiguous term, what we mean by weak and strong correlations. It's not entirely well defined, but the idea is that if you're weakly correlated, you're very close to being a non-interacting fermionic system, and if you're strongly correlated, you're very far away from this. So based on that, we've got a whole bunch of different concepts and different ideas in condensed matter physics, which I've put here, and we're going to take a journey that follows this this line here. So, for instance, at the weakly correlated side, you've got things like the free Fermi gas, and then if you add a random potential, you get an Anderson insulator. So that's basically disorder. And then you've also got add time reversal symmetry, and you've got topological insulators and things like this. If you add a little bit of interaction, so with the crystal potential, you can get band insulators. If you add a very strong repulsion on one lattice site of a problem, you get the Kondo effect. If you add a little bit of weak repulsion, then we can get ourselves to Fermi liquids, which we will talk about. And if you add a little bit of weak attraction, then you get to BCS superconductors. And if you add very strong repulsion on all the lattice sites of the problem, then you end up with the Hubbard model and Mott insulators, which is of course relevant to high temperature superconductors. But then there are other topics such as adding strong magnetic fields, getting you to the integer and fractional quantum Hall effects, or adding interaction and disorder together, you get something called many-body localization. So these are all kind of very, very common topics in many-body theory at the moment, especially many-body localization. That's a very hot topic at the moment. But we're gonna just follow this path over the next few lectures. So how to describe this stuff? Well, that's the purpose of this lecture, which is going to be starting in on second quantization, which is something that I'm sure that you've all heard of, and maybe some of you are already very happy with it. So I apologize if you know all this stuff already, but I thought that it was good to start somewhere relatively basic. So if we begin, we think about what a single body quantum mechanical problem is. And in general, what we were going to do is we're going to solve a quantum system, and it's going to have some Hilbert space associated to it of all the states that it can exist in. It's a single particle problem. It could be an infinite number of states that it could be in, but we'll just consider it to be capital D for now. And there'll be some basis of states. So there's a completeness relation between them. They're orthonormal, they're normalized and orthogonal, and they form a basis of our one particle space. And very often we'll be interested in infinite dimensions, so position, for instance, of a particle, and in which case the position states are such a basis, and we'll be interested in the amplitudes in that basis, which are the wave functions. So if we want to solve a single body quantum mechanical problem, we want to solve the time-independent Schrodinger equation. And in the language I've just said, that will be some D by D matrix with matrix elements in the basis of interest given by this. And in the case of the an infinite dimension continuous problem, we would instead get a partial differential equation. So something that looks more like this, for instance. And we want to solve this to find the eigenstates of this problem. And we obviously the examples, common examples, free particle in 3 dimensions, plane waves, or a 1D harmonic oscillator, you get Hermite polynomials times a Gaussian, etc. So these are all simple examples of one body quantum mechanics problems that you've solved before. So what about a many body problem? Well, a many body problem, we need lots of copies of our one body problem. And to do that, we need something called a tensor product, which is essentially we just copy our Hilbert space many times. And so we've got n particles, we're going to have n copies of these Hilbert spaces. And then how do we construct a basis that spans this full space? Well, we just do exactly what we would do in a single particle space. We just tensor product each of them together independently. So this is a basis state for particle 1, which is in this space. This is a basis state for particle 2, which is in this space. And this is the basis in this state. And if you add and sum all of these up, you get the completeness relation, and they are orthogonal already by virtue of being orthogonal in the single particle space. Yeah, which is this. Okay, they've inherited orthogonality. So what's the dimension of this massive space here? Well, it's whatever the dimension of the single particle space was to the power of n. So it grows exponentially with the number of particles. And this is a clear indication of the many body problem. If you prefer to think of things in infinite dimensions, so a continuous problem, the same difficulty arises, namely that if you look at the wave function of this many particle state, you're going to get products of all of these single particle. This is a basis wave function of in the many particle space, but now it's a function of r coordinates. So you've got a very high dimensional partial differential equation to solve. So it's essentially this problem again, the exponential growth. So if we want to deal with many body quantum mechanics, then we should probably think a little bit about what a single particle problem looks like in a many body setting. So let's look at a single part. So we've solved the single particle case. Let's see what would involve to solve the many body case. Well, we'd have this D by n matrix, this enormous matrix H, or we'd have this very large dimension PDE, and we want to solve that to find its eigenstates, which is solving this equation here. So if we want to do that, we need to be able to build this Hamiltonian first out of operators, and those operators are going to involve single particle operators, but they're also going to involve two-body operators, namely ones that describe interactions between particles. So what does a single particle operator look like? Well, that's just an operator that acts on one copy on this H1, so the small one copy of the Hilbert space. This is just an operator expanded. This is matrix elements. These are the outer product elements of the operator. And if we want to extend that operator into the many body space, we simply tensor product it with lots of identity operators, and then we shove in the A operator at the ith position, and that's the A operator acting on the ith particle. So it does nothing to any particle except the ith particle, and the action of that is given here. the AI just acts on the ith coordinates inside this basis state. So this allows us to construct a Hamiltonian for a non-interacting particle. We could have a Hamiltonian for a single particle obeying this, and we could simply elevate that Hamiltonian for a single particle to each particle and sum over all the particles individually, and then we end up with a many-body Hamiltonian for n particles, but they of course don't interact. And the eigenstates of this system will simply be products of the eigenstates of each single particle problem, and the energies will be the sum. So this is trivial, and this is the example of this is non-interacting particles which each obey the Schrödinger equation. Then we'll end up with this, and these could be products of Hermite polynomials or products of plane waves, depending on what this potential was here. So it's just a single particle problem n times. So that's a simple example. That's the easy case. But what we really want to solve is we want to solve this. We want to solve the sum of the single particle Hamiltonians, so the kinetic energy plus potential energy, but we want to add a two-particle interaction into it that couples the particles together. And then we want to solve this equation to work out its eigenstates. And that's a formidable task because of this thing here. So let's just have a look at that again. What is this? This is an interaction between particles. I've said that it's dependent on only the modulus of their distance. And what we've got here is we've got an operator that now acts on two copies of the single particle Hilbert space. And it will scatter particles that are in certain one particle states. It'll scatter them into other one particle states. That's the purpose of this. That's what this operator does. I'm using this curled notation here for a reason, this curl bracket here, and not the normal triangular bracket, which I'll explain shortly why I'm doing that. Okay, so if we want to construct a two-particle operator that acts on all pairs in our n-particle system, so we want to sum across all possible pairs. I'll put a factor of a half here for double counting, because I'm just using I not equal to j. Then I need to embed this. I need to work out how to act this on a particular pair of particles, and that's exactly what this equation here does. It picks two pairs of particles and it acts on them with this particular set of matrix elements. And if you then sum this over all possible pairs, we get all interactions that we need. Okay, so the approach that I've just advocated is not very nice, building up this huge Hamiltonian and working in this basis. And there are two problems. One of them is relatively benign. It's the particle number issue. You'll notice that all the operators that I constructed here, I had to know exactly how many particles I had to begin with. So I would have to reconstruct my Hamiltonian for any different particle numbers I wanted. I would have to reconstruct all my operators for a specific particle number. And that makes this theoretically a bit awkward, because we might want to extrapolate the number of particles from some finite number to an infinite number. So the thermodynamic limit. So that makes it a little bit awkward, but it's not a fundamental problem. What is a fundamental problem is that this formalism that I've introduced doesn't deal with identical particles very well. And it's a bit of a thorny issue. And to show that, let's just recap some stuff that I'm sure you're already very familiar with, that electrons are, of course, identical particles. And that means that the operators and states should have some specific behavior under the permutation of their quantum numbers and coordinates. So the operators, like the Hamiltonian, should be invariant to the exchange of particles. But the states themselves may change up to a sign, as I'm sure you're aware. So what we've got here is we've got an operator that will take whatever particle, whatever state is here, and swap them. Okay, that's all it does, just swaps the two states. So this particle is in some single particle state, this one's in here, and then it'll swap them, so this one's here, and this one's here. Okay, and this is completely defined easily in our basis just by swapping the two labels, the I and j label. And that's the exchange operator. And if we take any wave function, then if we apply the exchange to it, it's just exchanging their arguments of the wave function. Am I on mute, or have you, someone can hear him? Okay, good, you can still hear me. Okay. Maybe it's when I move the screen a lot, it uses bandwidth up or something. So applying this operator to a wave function just swaps its arguments, the ith and jth arguments. And because this operator, if you apply it twice, it just goes back to where it came from, then it must have eigenvalues of plus minus 1. And it's a Hermitian operator as well. And so you can use the exchange operator to build up permutations of particles. Say, for instance, like this, strings of permutations. And we will denote the number of exchanges inside a permutation as the modulus of this thing. Right, so as I'm sure you know, particles come into two different varieties of fermions and bosons, depending on their spin. This is spin statistics theorem. And this tells us that the wave functions of many fermions, they behave the same for all exchanges. So they have the same behavior, the same eigenvalue for any exchange of particles. And in the case of fermions, the eigenvalue is -1. So you can perform any exchange of any pair of particles and you always get the minus of the wave function back. And for bosons, you can perform the exchange of any pair of particles and you always get plus sign. For those of you who might have thought about this a bit more, you might ask the question, why can I not have a wave function of particles that is a plus for some exchanges and a minus for others? And this gives you something called weird thing called parastatistics, which doesn't appear in nature. In nature, you only get one or the other. It's either always -1 or always +1, or you can sometimes get a phase factor if you've got what's called an anion. But we're not going to talk about that today. Now, the corollary of this fact is that if you set any of these two arguments the same, fermionic wave functions must vanish, and that's just the Pauli exclusion principle. Now, this places very, very, very strict exchange symmetry constraints on what a physical many-body wave function must look like for identical particles. So if we go back to our basis, where I specified that particle 1 was in this state, and particle 2 was in this state, and particle n was in this state, this is equivalent to this wave function here, which is the product of the wave function alpha 1 for particle 1, alpha 2 for particle 2, ... alpha n for particle n. This is not a physical wave function, which is why I've drawn a line through it, because we can't ascribe specific states to specific particles. So what that's telling us is that this Hilbert space that I built, that was the product of all of these Hilbert spaces, is far too big. It contains many states in it that are not really physical states. So in order to do that, we have to project this Hilbert space down, so we deal with either totally symmetric or totally anti-symmetric states. And what does that look like? Well, we can do that. We can build a projector that projects down into the relevant subspaces by, if we do the sum of all possible permutations of n particles divided by 1/n, this is in fact a projector. And if we do the sum of all of the permutations and we multiply it by -1 times the order of the permutation, we get the totally anti-symmetric projector. And if you want to prove that these really are projectors, that means they must obey this property if they're actual projection operators. You can do that because the permutations form a group, the Pn group, the group of all permutations of n objects. And what does this do? Well, you can take a state inside the full Hilbert space that's not physical, and you can project it down with this operator into this subspace of symmetric n particle states. That's where bosons would live, and you could take it and you could potentially project it down into the anti-symmetric case. Sometimes this projection might be 0. For instance, if it may not be able to anti-symmetrize a wave function. There are some states that you can't anti-symmetrize, as we'll see. And I'll notice also I've drawn the anti-symmetric subspace smaller than the symmetric one, and we'll see why that's the case shortly. So that means that if we want to have physical states, we should symmetrize many particle states or anti-symmetrize them. And by construction, because we've anti-symmetrized them, we will always get a -1 if we do any exchange in the case of fermions, or we'll get +1 for bosons. Okay, so let me see. Yeah, so what I'm saying here is we can make some general observations already. Let's suppose we repeated a quantum number. So we put two particles in the same single particle quantum state. We can show, using the properties of permutations and anti-symmetrization I just said, that if you do that, if you have two particles that you've specified that are in the same single particle quantum state, that if you try to do the anti-symmetric projection of them, it goes to 0. And again, that's just the Pauli exclusion principle. If you're going to have fermions, every fermion has to be in its own distinct quantum state with distinct quantum numbers. Otherwise, it will not get projected down to the anti-symmetric subspace properly. That's the Pauli exclusion principle. However, the symmetric case doesn't have that. You can put, every boson can be put in exactly the same state if you wished. And you can put them all in the same state, like here. This is already symmetrized. This state cannot be projected down to an anti-symmetric subspace. So that's one of the examples that gives you 0. This is effectively a Bose condensate. It's got where I put a macroscopic number of particles all in the same quantum state. And it also shows you why Sn is larger than An. You can always anti-symmetrize any state that's anti-symmetric has a symmetric partner, but not every state that's symmetric has an anti-symmetric partner. It doesn't work that way around. So this is definitely bigger than this. Bosons have a bigger Hilbert space to live in than fermions, which explains why they can both condense. Okay, here's some relatively trivial examples for two particles. I can create the symmetric and anti-symmetric projections easily out of them. And if I apply them to putting two particles in two different states, there you get a symmetric version and anti-symmetric version, which differ by a minus sign. And if you work out their wave functions, of course, it's just the sum or the difference of the wave functions with the two arguments swapped, because that's what that operator did. And they're exactly the kind of things you would have encountered when you solved the helium atom or the hydrogen atom. What about a slightly more tricky example? What about 3? This shows you already for 3 particles, life gets a bit more complicated. We now have 6 different terms in our projection and anti-symmetric and symmetric projection, and they have these different orders. And if you do that, it means that if you put 3 particles in 3 different states and you symmetrize it, you get this big long list of different permutations. And likewise, you anti-symmetrize, you get this one with 3 minus signs there. Okay, you can already see this is getting pretty tedious. Symmetrizing and anti-symmetrizing wave functions is not a very nice thing to do. In fact, it's growing factorially with the number of particles. So we'd really like to avoid that. A nice way of dealing with them doesn't get over all of the issues of difficulty is to notice that for fermions, the minus signs come about precisely because of the permutation, the -1 to the order of the permutation. And you can generate this by basically taking the determinant of a matrix. A determinant of a matrix gives you exactly that factor, and it gives you the product of the various elements inside it. And this is the Leibniz formula for a determinant. So if you had a wave function that you wanted each fermion in a separate single particle state, and then you anti-symmetrized it, that's exactly like putting all of the wave functions in this big matrix and taking the determinant of this matrix, and it's called a Slater determinant for that reason. And that would generate all of those complicated terms that you have there. But it's a pretty nasty expansion for anything more than a couple of particles. If you want bosons, you do exactly the same thing, but instead of taking the determinant, you take the permanent of the matrix, which is basically the same thing with positive signs. Okay, so let's get to the moral of the story here. First quantization generally sucks. So it's a very unpleasant formalism for dealing with identical particles. I say that with one caveat. First quantization is still used occasionally. For instance, when Laughlin worked out the fractional quantum Hall effect, he used first quantization to do so. So it can be useful in some contexts, but generally speaking, first quantization is a bit of an unpleasant formalism because of this anti-symmetrization business. So why do we need second quantization? We need it because we really like to find a description that doesn't depend on the number of particles that we have. And in some cases, we're going to want the number of particles to not be fixed. So it really would be good not to have this n dependence explicit in our equations. And secondly, we'd like a more painless way of dealing with anti-symmetrization without having to write out n factorial terms, because this gets pretty boring pretty quickly. Okay, so that's what I'm going to now explain to you, which you've probably already heard before, which is second quantization, which deals with this in an algebraic way. So let's just let me just recap on notation. I've been using this curly bracket here, like a quantum state with a curved bracket, for a tensor product of distinguishable single particle states. Okay, that's the big Hilbert space. And then I've used a normal ket symbol with an S and A on there to denote a physical state, which is symmetrized or anti-symmetrized. I'm going to drop the S and the A because it's obvious from the context whether it's symmetric or anti-symmetric. And I'm going to use the normal ket notation for a physical state, and I'm going to use the curve notation for an unsymmetrized state that's not actually physical. So there's our tensor product of states, and there was a specific ordering that we used these labels here. That ordering was the order in which we tensor producted the Hilbert space. So this is particle 1, that's particle 2, that's particle n. And we allowed them to live in one of d different single particle states. So the ordering had meaning here, meaning that different permutations of them were different states, okay? But for physical states, we know that the ordering is not relevant because we summed them all up anyhow with permutation signs on them. So up to a sign, the ordering of these numbers inside a physical state is irrelevant. It will at most give you a sign factor coming out in the case of an anti-symmetric if you decided to shuffle them around. That means that we've got a freedom in what order we decide to write these numbers, the different occupations, which single particle states we're going to put particles in. And the best way to do this is to use a canonical ordering. Once we've got it, we should fix it and then stick to using that, which means that we've got state 1, state 2, state 3, all the way to state D, single particle states that we could put particles in. And we decide to order them in ascending order. And that means that your numbers would look like this. How many times you put a particle in particle? You put particles in state 1. You put 1, 1, 1 a certain number of times, you put 2, 2, 2 a certain number of times, 3, 3, 3 a certain number of times. You've got them repeated, potentially, if it's bosons. If it's fermions, obviously they can't be. And then you can count the number of times these occur and use this as your label for your basis state. It's called occupation number representation, and the crucial part of occupation number representation is that it only uses information that you actually know about the state. That is, that it only uses the fact that you know how many particles are in a given single particle state, but you don't know which particle. So it's got the correct physical description. It's not redundant. It's not got additional redundant information in it that you can't actually know. So Ni is now the number of particles that are in a particular single particle state, J. Okay, good. So naturally, if you add up all of the occupation numbers, they should add up to n because we had n particles. But in principle, that's a number that could be varied as you wish. Whereas this thing had n different indices. The n was kind of fixed in the state. This same representation can be used for any number of particles because it's now, that's the number of particles is just a constraint on what the sum is. Okay, so we've traded the need to track n single particle labels for D, the dimension of the single particle Hilbert space, occupation numbers, which could be infinite still. And we only describe what can be known, and we've removed unphysical redundancies. So what we've got is, we've got an occupation representation of the symmetric subspace. The occupation numbers can be anything, And in the antisymmetric subspace, we know that the occupation numbers can only be 0 and 1. That's the Pauli exclusion principle. And as I said, it doesn't depend, our basis doesn't depend explicitly on the number of particles we have in a system. All right, this is a bit of technical stuff which I'm going to skip. Basically, I'm just showing how do you normalize, when you project a state, an unphysical state into its subspace, you need to renormalize it because it loses norm in general. And this just shows you that when you normalize these states for fermions, you end up with this 1 on root n factorial in the front of it. And if you do the same thing for bosons, you end up with a slightly more complicated set of factorials for the properly normalized bosonic and fermionic states there. Okay, so a more interesting thing now is we want to build what's called the Fock space, which is named after Vladimir Fock, who which is essentially telling us all of the different particle number spaces that we have available, and we're going to basically sum them all up, and it allows us to build a set of basis states that spans all possible particle numbers. And the really neat thing that this does is it introduces something that looks pretty trivial, but actually is quite a subtle idea. It introduces a quantum state that has no particles in it. So it introduces the vacuum. And that might seem pretty trivial, but actually it's a really, really important step, one that you would never have even thought of in first quantization, because in first quantization, you don't have a wave function if you don't have a particle. Whereas in second quantization, we actually have a quantum state that represents the system with no particles in it. And that's really crucial because we're going to use that to build all of the other spaces, all of the other states that we have. So we have a single particle space. That's where we've got a 1 in one of the single particle states available to us. And so you've got many of them that we could go down. And obviously the symmetric and antisymmetric subspace are exactly identical. They're the same here. There's only 1 particle. But if you go to 2 particles, then of course you can only put in the antisymmetric space. You can only put a 1 in one of the. You can only put 1 in any one of the single particle states, and then you've just got all the different ways you can distribute the 2 particles by not putting them in the same state. But if you've got the symmetric subspace, you've got all of those states plus all the ones where you stuck 2 particles in the same state. So it's slightly bigger again. Okay, so if we add up all of these spaces, these total particle number spaces, we can add them all up for 0 to infinity number of particles. We end up with the Fock space of bosons and the Fock space of fermions if we add up the symmetric or the antisymmetric. And they're all spanned by the same occupation number states with unrestricted total numbers. And as I said, there's curious features of this is that we have a vacuum state now, which is slightly weird, and we have an orthonormality between states that are between the occupation number states. If they exist in different subspaces, then if they exist in, say, for instance, if this had n particles and this had n plus 1 particles, they would automatically be orthogonal to each other. Okay, so they've inherited that. And we can create arbitrary states which could be in principle superpositions of different particle numbers, just by having amplitudes that exist in the spanning the different Fock spaces. Now, in reality, physical states of systems tend to exist in one Fock space, and this is because we have charge and mass superselection rules that prevent you from having a superposition of having 1 particle and no particle. Okay, or 2 particles and 3 particles. So generally, quantum states really must exist inside a fixed number space. But there will be occasions where it's quite useful as a theoretical tool to allow for superpositions between having different numbers of particles. And a Bose condensate is a particular example of that, where it actually is theoretically much easier to explain and to compute properties of if you allow for particle number violation. Instead of you having a fixed number of total particles, you have a spread, you have a distribution of particle numbers. So it is actually useful to consider even superpositions of different particle numbers. All right, let me quickly introduce the tools which I know you've all heard of before, which is creation and annihilation operators, but using the kind of language that I've been developing here. So it's easiest to deal with bosons first, because bosons basically are just harmonic oscillators, is the moral of the story. You define a creation operator on a bosonic mode, on a particular mode I, as being the one that just simply adds one to the particle, one particle to that occupation number, and multiplies it by the root of ni plus 1. Okay, and the reason you use ni plus 1 will become clear soon, but it's basically because it's a harmonic oscillator. And that means that every time you apply the AI dagger operator, you move from one up on the particle number subspaces. And because it's bosons, you can apply it multiple times. So you could, in principle, just keep moving up and up and up and up and up and adding more and more particles to the same single particle mode. So you can daisy chain the creation operators on top of each other. Now, having defined, since quantum mechanics is basically linear algebra, we've defined the action of this operator on a basis, so we know exactly how it works. We should also look at its conjugate, which is the annihilation operator. And we look at that by just simply taking the conjugation of this equation, which gives you this. And you can read off from this that an annihilation operator must reduce the particle number by 1 and multiply it by the square root of n. Okay, so it just looks exactly like a lowering operator on a harmonic oscillator. And likewise, you see that if there was no particle in that state to begin with, if ni is 0, then this kills this side of the equation. So you can't take a particle out if you didn't have one in there to begin with. Okay, and that's ultimately why we stuck a n plus 1 originally in the A dagger, in order to reproduce the fact that the vacuum kills. Annihilation operators kill the vacuum, or they kill the empty state for that particular mode. Okay, so we introduce the vacuum state, which has no particles in any mode. So actually the vacuum is then a unique state because it is killed by all of the annihilation operators. Every annihilation operator gets killed when it hits the vacuum. And that makes sense because there's no particle to go to if you keep going down the ladder by doing an annihilation operator. And then a nice combination is A dagger A on the same single particle mode. That's just a number operator, so that just multiplies the state by the number of particles that's in that mode. And that's true for fermions as well. Okay, so we've introduced these nice operators, but we should work out, since they're operators, we would really like to know how they commute, or what algebraic relations they have to each other. And it turns out that they actually have a very nice relationships to each other. In particular, for bosons, it's extremely nice. Basically, everything commutes is the short, except with itself. So if you've got two different operators that act on different numbers, it doesn't matter what order you apply them in, you get the same answer. So that tells you that two creation operators on different modes, they commute with each other. And in fact, it's still true even if they're the same mode, sorry. It doesn't matter it's trivially true if you apply it to the same mode. So all creation operators commute amongst themselves, all annihilation operators commute amongst themselves. The only case we have to consider is if you have a creation annihilation operator. And in this case, they completely commute with each other as long as they act on different single particle modes. And if they act on the same single particle mode, then you don't get, they don't commute with each other. You can work out what the answer is by working out this result, and you see that these two differ by 1, and that's exactly this commutation relation, which you should recognize is just the commutation relation of harmonic oscillators. So bosons, bosonic creation and annihilation operators share the algebra of harmonic oscillators, which is exactly as expected because we kind of basically built them to do that. Okay, so given that you've got a vacuum state and you've got a creation operator, we can now build the whole Fock space using creation operators. And that's because we just take the vacuum And if we apply a creation operator to the vacuum on site for mode I, we put one particle in exactly that mode, and there's no particles anywhere else. So that's a one particle state. And for all different values of this I, we get all the different single particle states. And if you want two particle states, you just do two creation operators, where you put one particle in one mode, one particle in another, or you put the same particle in two particles in the same mode, and then you pick up a slight normalization. You just pick up an extra factor of √2 here. And that means that if you apply, you can build any occupation number state by just simply applying the relevant creation operator in whatever order you like. It's completely irrelevant what order these are in, because they're bosons, they commute. And you simply raise it to the relevant power, and then you divide by the root of the number of n factorial of the number of times you applied it, which gets rid of these factors like this or like this. And so that is a number state, a Fock state of bosons. Okay, bosons are fine, but fermions are what we're really interested in, because they obviously describe electrons, and they've got a slightly more annoying property to them. So what we've got here is that I've defined what a fermionic creation operator does. And what do we expect it to do? Well, we expect it to act on a particular single particle state, the number of that state, and increase it by 1. But we know that you can only have ni equals 0 or 1, which means you can only add a particle if it didn't have one in it already. So there must be a factor of 1 minus ni in there. So this must vanish if the particle is already, if there's already a particle in there, you can't add another one, so it must kill it. So there must be a factor of 1 minus ni in front of it, and then you must increase the particle number. What's this thing? It looks pretty complicated, but it's summing the number of particles between 1 and just before, so all the number of particles that are in this state up to the one that you just applied the creation operator to. And it's -1 to the number of particles that are there. And it's called a Jordan-Wegener string. And the reason for it will become clear very shortly. But basically, it's to make operators anti-commute with each other. Okay, as I'll show you just shortly. So what happens here now is that we can apply CI, and we can go from no particles to 1 particle, but we can't daisy chain many CIs on top of each other, because you can only put 1 particle in the mode. So CI will connect all of these sectors, but you can't, I put this line here to indicate the fact that you can't daisy chain them like you did with bosonic operators. Good. Okay, we could take the Hermitian conjugate of the creation operator that we defined, and we'll get the annihilation operator, and its action is just simply annihilate a particle, and clearly it must have a factor of ni in front of it, because you can only annihilate a particle if there's one in there to begin with, and you need it to vanish if it's empty. So if its ni is 0, this equation vanishes, and it has the same Jordan-Wegener string there. Good. And you can check that they are in fact the adjoints of one another, which is what they should be. So just looking at the matrix elements. So the definition I gave you is a correct definition. Is mathematically correct. And creation operators, of course, lower you down this ladder of different spaces. Sorry, annihilation operators. Okay, so now we need to work out what properties these operators have that I've just defined. And a good one to look at is this one, where we don't have a particle, we add a particle into a state to get to this, and then we remove the particle from the state to get to this. And what you see is this basically does nothing to it just gives you back the original state. If you had 0 particles in it to begin with, it just gives you back exactly the state multiplied by 1. If you had 0 particles in it and you applied this though, then you would get 0. Because it didn't have a particle in it, you can't annihilate a particle from it, so it gives you 0. Likewise, if you do the same calculation, but you stick a particle in Ni, then this one now gives you back the same state. When it has a particle in it now, the number operator C dagger C gives you the same state back, and the inverted ordering one gives you 0. And that's telling you that there's a non-trivial relationship between these two operators, and it's not a commutation relation. The commutator is not trivial, but the anti-commutator is. So the anti-commutator is the sum of the two. And the anti-commutator, if you add these two operators up, is just the identity operator. It does nothing to any state that it acts on. Okay, and that's fundamentally telling you that there's something about anti-commutators that fermions prefer. Okay, fermions are described by anti-commutators rather than commutators that are describing bosons. And the reason for that will become very clear. It's because of the minus sign in their symmetry under permutation. All right, so what's this Jordan-Wegener string doing? Because this was for two operators that were in the same mode, I. Well, the Jordan-Wegener string is basically just establishing that if I have two different operators on an annihilation operator on mode J, on mode I, and a creation operator on mode J, where I and J are different, it's just establishing that they must anti-commute. So it's basically making all the operators anti-commute. Because it's a zero here, their anti-commutator is zero. Whereas here, their anti-commutator was not zero, it's one. Okay, so that's a very non-trivial relationship because it's got a one there. But all the other operators anti-commute with each other. So fermionic operators on different modes anti-commute. So creation operators themselves anti-commute, annihilation operators, and the combinations of annihilation and creation operators, as long as they're on different modes, anti-commute as well. So everything anti-commutes basically with fermions except this one here, which is equal to 1. Okay, just like with bosons, we build up many fermion states by applying in a particular order. It must be ordered, and you must have fixed that ordering, and you must keep that ordering once you've fixed it, because it's important. You basically add particles to the states, and here I've chosen the numerical ordering. If you decided to do it in a different ordering, you'd get the same state, but you might have a minus sign in front of it because you've got the ordering the wrong way around, and it's a different permutation. Okay, this is just, I'm not going to go through this. This is just basically linking the number representation to the previous representation we had in terms of explicit numbers, particles being in specific states. And it just basically confirms that if you apply the exchange operator on a number representation, it's basically just exchanging the ith and jth creation operator in the string that creates the state. It just swaps them around, and you see that because it swaps them, then you need to anti-commute them to put them back in their original ordering, and you always pick up a minus sign from this. So basically it proves that because of the anti-commutativity of creation operators, it creates the correct exchange statistics that you need. Namely, that fermionic anti-symmetrization is precisely why we must have anti-commuting operators, and boson symmetrization is why we must have commuting operators. All right, so what has all this got us? We dispensed with first quantization. We now only consider number states, so Fock states with occupation number representation, and we've got creation annihilation operators to allow us to create particles from the vacuum, create different single particle, two particle, three particle, etc. states. And we've got rid of all that permutational complexity of anti-symmetrization, and we've embedded it into the algebra of either commuting operators for bosons or anti-commuting operators for fermions. And it's all handled automatically. Like I just did up here, right? When I did it here, everything was handled automatically. I have a different permutation of particles. I get the minus sign for free because the operators anti-commute with each other. I didn't need to work anything out. It was just it was intrinsic in the formalism. And I've got a description that's not tied to the number of particles, total number of particles. To finish this program, which will finish what I'm going to say for this part, for this lecture, we need to show how to build operators in this second quantized formalism. Okay, and then we've got all the tools we need. We've got the states and we've got the operators, and we've got everything we need to describe a many-body system with second quantization. So just to recap, for fermions or bosons, if you have a one particle, this is an operator that acts on one particle. It acts on a one particle Hilbert space. If I wanted to act on the full many-body Hilbert space of n particles, which was unphysical, the massive one where we have one Hilbert space for each particle, then we just simply put the operator in there, the single particle operator, and we put all of the identities everywhere else. And if we want it to be a physical operator, then we must make this operator must be symmetric under any exchange of particles, which means it must be the total sum, the equal sum of it being acting on any particle. So basically, the many particle version of this operator must be the sum, the equal sum of all of it acting on particle 1, particle 2, particle 3, all the way to particle n. And that means it's a symmetric operator. All physical operators are symmetric under exchange, whether they're for bosons or fermions, they have to be symmetric. The states can be anti-symmetric or symmetric, depending on whether they're fermions or bosons, but the operators must be symmetric. Okay, so this operator AN that I've just described, it has matrix elements that look like this. Okay, so it can act on, so we're summing over I, which I acts on, and we're summing over then the Hilbert space of single particle. So that's why it's got this double sum here. And this is the unphysical space, remember, of the full unsymmetrized version. But we could just go ahead and symmetrize or anti-symmetrize it. And all we would do is to just change this state to be symmetric and this state to be symmetric, or this state to be anti-symmetric and this state to be anti-symmetric. So the same formula applies for the symmetric and anti-symmetric version. What I want to show now is the second quantized version of this operator, which had a particular particle number, is just given by this nice equation here. Okay, it takes the single particle matrix elements, the same ones that appeared up here, and all it does is it applies C alpha dashed C dagger alpha. So it annihilates a particle in a particular mode alpha dashed and creates one in alpha, and it does so with this amplitude. And that's a really nice, that's a single particle operator. And it can be applied to any number of particles. You can apply this to any of the occupation number states we had. Doesn't matter how many particles there were on it, it had in it. Okay, so how do I show that this is the same as this and this? Okay, well, the way to do that, I'll just sketch it out for you. You can go through the details yourself if you really want to know. But basically, you just use the commutation relations or the anti-commutation relations between creation and annihilation operators, and you show that what the commutator is of A with a particular creation operator, another creation operator. And you get this final answer here after doing a little bit of algebra. And this applies for fermions and bosons. So if you take a full number state this is an occupation number state. I've just decided to write it with all of these numbers explicit here, with all the different modes that you put the particle in explicit. If you now apply this operator to this state, what do you get? Well, you use the commutation relation of A with each creation operator. So you first of all apply it to this one to shuffle it around, and then you apply it to this one. So you end up with this chain of commutation relations until you get to the end here, where you use the fact that it disappears on the vacuum. So why does A disappear on the vacuum? Because if you remember, A has an annihilation operator on this side. So if it ever hits the vacuum, it equals 0, okay? Because it's got an annihilation operator here. So because A vanishes on the vacuum, you've got this expansion of commutators. And if you write that out, you get exactly the same equation that we got. You get this double sum and all of these matrix elements over all of these states, the appropriate anti-symmetric or symmetric states. So that's exactly what we had here. Okay, so this reproduces it for us in a much simpler way, and that just proves that it does. Here are some examples. The number operator is the simplest example. Count the number of particles that are in a particular state, and we already know what that is. It just looks like this. So it's a really simple one particle operator. The number density, for instance, if you're using the spin and position representation, that would be quite simple as well. That would just be the sum over all the spin, all of the two spin configurations, and it would tell you the the total density of particles at position R. And you can have a spin density, which is a little bit more complicated because now you need to have a Pauli matrix elements between them. And they're all single particle operators because they're bilinear. They involve one creation and one annihilation operator. I'm going to quickly discuss two particle operators, and then I'm done for this lecture. So we obviously need to be able to describe this thing, which was the really difficult thing that we mentioned earlier. These are the unsymmetrized matrix elements, and this acts on two different copies of the single particle space. If this is a physical interaction, it has to be invariant under exchange, which means that these matrix elements, in fact, must obey this constraint. So the interaction doesn't care which particle is which. It shouldn't do. No physical interaction should between fermions or bosons. So I'm just going to sketch it out, but the basic strategy is exactly the same. You elevate this operator to an operator on the full Hilbert space that's unphysical. You then project it down to the symmetric one. It's describing the interactions between all possible pairs of particles in your system. And the action of that operator on any symmetric or anti-symmetric state is given by this double summation here of all possible pairs and then all possible matrix elements that connect them. And the final answer, if you convert this into second quantization, I'm just going to give you here. And there's two things to note about it. First of all, there's a factor of a half in front. The same matrix elements, notice these are the unsymmetrized matrix elements. They're the matrix elements assuming particle 1 is in state alpha and particle 2 is in state beta. This is often how you compute integrals, like Coulomb integrals. You often don't have the symmetrized states in there. You have the unsymmetrized, unphysical state matrix element. And notice that the order of the beta and the alpha dashed here is opposite to the order here. And that is because if you want to annihilate the state where the first particle is in alpha and dashed and the second particle is in beta dashed, you need to annihilate them in the opposite order you created them. And that's the reason why it's backwards here. Okay, so they're just the two things you need to notice. And this is a second quantized version of an operator that will scatter particles from one particular state, and the interaction will scatter the two particles into two different single particle states. Okay, so this is the sketch, which I'm not going to go through, but if you want to know why that reproduces the correct interaction, then you can follow exactly the same method that we did before and get to the final answer using commutators. It's just a little bit more complicated than it was in a single particle case. And you'll end up confirming that that is indeed the correct expression for a two particle interaction that's generalized to second quantization. Let me just finish with an example. An obvious one would be a spin-dependent two particle repulsion. And this is given here. So we've got some repulsion between the particles. The particles don't change location. So if they're in R1 and R2, at the beginning of the interaction, they stay in R1 and R2 at the end of the interaction. So there's delta functions, and the interaction is independent of spin. So there's deltas on spin as well. Spin doesn't get flipped or anything by a simple spin independent interaction. And an example would be the Coulomb interaction. And if you did that, you would stick, that is exactly the unsymmetric matrix element of the Coulomb interaction, and you would stick that in here and you would integrate over the positions. And this is the second quantized version of a raw unscreened Coulomb interaction. Okay, good. So that's where I'm going to finish for this first lecture. Hopefully, I went through it pretty quickly, but we just looked at second quantization and basically how to handle many identical particles. What I want to show you in the next lecture is how to use this to do some useful things, some useful calculations. And in particular, we're going to look at three different things. We're going to look at what it means to diagonalize a one-body Hamiltonian. We're going to look at Hartree-Fock, and we're going to look at BCS theory, written in second quantized formalism. But for now, I think we should have a break because I've been talking for a long time, and maybe come back at 11 o'clock. Does that sound good? Or I've got questions. If you've got questions, you can ask me questions. But otherwise, we can have a break now, go and get a coffee or something, and come back at 11 to just finish the next part. Anyone still awake? Yes, you're still awake. Good. Okay. All right. We'll come back at 11 o'clock. I'll start again with the next lecture. Okay. I'm going to start again now on the second lecture. So we spent the first looking at second quantization and building up the formalism we need. And I wanted to spend this lecture applying those tools to get to some relevant examples to you. So, I mean, I imagine a lot of the content of this course is the kind of thing that may not appear in your research directly right now, but from past experience, I've found that students quite like coming back to this material when they're writing up their thesis, because it's quite useful for your background theory in your thesis. Some bits of it may be useful for that. And I think that this particular lecture might contain some useful things for that. So yeah, we're going to do this today. We may not get through all of it, this lecture. I'll stop at 12, wherever I get up to, and we'll continue next week with the rest, because I don't want to overrun. And we have enough time in future weeks to finish with the course. Okay, so let me just recap again what our basic problem was. We would like to solve a Hamiltonian in second quantized formalism that looks like the following. It has a single particle term, because it's bilinear in creation and annihilation operators, with some amplitudes. This is basically the single particle kinetic energy and potential. So it describes everything from the presence of magnetic fields to the band structure of your problem. Everything you would do would be inside here, inside this term. And this is the two particle term, which I flashed up at the end of the last lecture, which is in a generic repulsion term between electrons, with some matrix elements that we need to compute for whatever given orbitals we have in our problem. But it will have this form, and it will generally be quite difficult to deal with. And we've used creation annihilation operators with some particular set of single particle states, which I've called alpha, which I introduced in the previous lecture. So we're going to concentrate for the moment in this lecture, or at the beginning at least, on the single particle term, because there's a lot of important physics to understand about the single particle term, which will then help us to try to solve this thing variationally. Okay, and we're going to come up with a simple variational mean field approach to the full problem, and that's going to be Hartree-Fock, and it's not terribly accurate, but it's quite a useful approach nonetheless. It's kind of the 0th order approach that you might do to solving an interacting problem. And we'll also look at the BCS theory. It's what we're going to do. But before we do that, we have to consider what it means to diagonalize a single particle Hamiltonian and what it means to change our single particle basis. So we had our Hilbert space of one particle, and we started off with this alpha basis, which we could draw here, but we could equally rotate our basis into another set of orthogonal states that spans the single particle's Hilbert space. So we could go from this set alpha to the set K. It's another orthonormal basis. It's connected, the two bases are connected by a unitary transformation. So there'll be some unitary matrix that will be a D by D matrix, if this is a D-dimensional Hilbert space, that tells you how the K basis vectors are built up out of the alpha basis vectors. And the unitary is exactly that. It maps each basis vector between the two basis sets. And unitarity means that U dagger U or U dagger equals identity, which is basically these equations here, written out in terms of matrix elements. And you've also got the inverse transformation, which tells you how the alphas are written in terms of the Ks, which is just given in terms of the U dagger matrix elements. Now, we defined our creation operators were pinned to a particular choice of single particle basis. So C alpha created a single particle state with a particle in the state alpha, but we could equally well create a new creation operator, which we'll call D dagger K, which creates a particle in the state K. Okay, it's a different single particle basis. There's no reason why we can't do that. So how do we change our single particle basis? Well, we've just said I introduced dk dagger to be precisely the to create the state K from the vacuum. And then if you look at this, it's a superposition of the alpha states given by this U, whose elements are the elements of this unitary matrix. So our new operators are just unitary superpositions. Our new creation operator, dk, is a unitary superposition of the creation operators in the alpha basis. So we get this for the creation operators, and then we dagger it to get this. So we have to flip it around in order to get the annihilation operators. If you have a unitary mixtures, if you take any set of single particle, any set of creation operators and unitarily mix them amongst themselves, you will get a new set of creation operators and a new set of annihilation operators equivalently. And those, as long as you use a unitary, those new operators will be valid fermionic operators. What do I mean by that? I mean that they will obey all of the same anti-commutation relations that we derived in the last lecture for the C alphas. And how to show that? Well, you just shove these into the anti-commutator here and expand it, and you'll see that you end up with what is effectively, if you go back to here, you use these relations which tell you how, which is the expansion of a matrix multiplication for U dagger U or U dagger. If you stick that in here, you'll see that you collapse this to a matrix product, which itself becomes the identity matrix, which is just a delta. So it's telling you that these are canonical fermionic operators again. Okay, so we've just changed the single particle basis. So I've got this T term in my Hamiltonian, the single particle term, and it has matrix elements that were given by these terms here. So it's a D by D matrix, and I'd like to diagonalize it. So what does that mean? Well, in linear algebra, a diagonalization means that you decompose the original matrix into some unitary matrix times a diagonal matrix times the dagger of the unitary matrix. So the unitary matrix contains, whose columns contain the eigenstates, and the D, the values along the diagonal are the eigenvalues. So we take a dense matrix, which has got off diagonal and diagonal elements. We diagonalize it, so we end up with some unitary, or if we sandwich the unitaries, U dagger U on T, we would turn it into a diagonal matrix. We'd cancel these out, and we would turn it into a diagonal matrix like this, whose eigenvalues are the eigenenergies of the system. So this unitary U that we use to diagonalize the matrix T is exactly a single change in single particle basis. So it's going from this basis where alpha, the alpha basis, where the T matrix was dense, to this basis, which is the K basis, where the matrix is now diagonal. And if you take the term in the Hamiltonian, the single particle term, this is a general single particle term. It's got off diagonal elements. And then you insert this decomposition into this equation and expand it out. Then you can pull the U's and the U daggers, and you see that they're exactly the definition. This is D dagger K, and this is dk. And so what you've ended up with is you've ended up with this. This is what a diagonal Hamiltonian looks like in second quantization. It's a sum of number operators. These just count the number of particles that are in any given single particle eigenstate. which is exactly what this basis is. It's the eigenstates of the T matrix. So that's what it looks like. And we would love to get everything into that form because it's really easy to deal with diagonal Hamiltonians. Here's a really simple example, just to get you back to some real system rather than totally abstract ones. Imagine you have a lattice, a one-dimensional lattice of ions, where we've got some potential in which we can stick a particle in that lowest state in that potential. And it might look like this. If we stick the particle in, it might have a wave function that's localized but spread out. And because it's spread out, it overlaps with a neighboring one. So there's some hopping matrix element between them. So we basically have a type binding, 1D type binding lattice that we imagine has got periodic boundary conditions wrapped around with some finite number of lattice sites, which I've chosen to be 0 to m-1. M is the number of lattice sites. And we end up, you could write that Hamiltonian in single particle first quantized form in terms of single particle states. You could write it as this, okay? And we need to diagonalize this matrix. It's not diagonal. It's got off-diagonal elements to it. And it's easy to diagonalize this because of its translation invariance. We can use quasi-momentum states. And if we choose m is even to avoid some tedium, basically you have single particle states which look like this. They're just plane waves. Plane wave superpositions of the particle being in one lattice site. So the basis we're using here is a particle is localized on a given lattice site. That's the basis we're starting with. And then we're going to move to the quasi-momentum basis labeled by K, where K is the quasi-momentum, J is the location, and A is the lattice spacing. That's this spacing here. And K is the, I there is, of course, just the imaginary number. And if you do this, you need certain values of K to diagonalize it. They're given by this sequence of K's here. Notice we don't have m on 2. It's m on 2 minus 1 minus m on 2. That's because those 2 points, m on 2 and m and minus m on 2 are the same point. So, so you don't have it twice. And if you do that, you will diagonalize the Hamiltonian and get this cosine dispersion relation. So what we've done is we've taken a Hamiltonian that was basically had zeros along the diagonal and had bands along the off diagonal, nearest neighbor hopping, and 2 terms at the edges, which was the periodic boundary conditions, and we've diagonalized it into something that's got this cosine structure going along the diagonal. And that's what we've managed to do. And so in second quantized form, you've taken this, which is a nearest neighbor Hamiltonian, you've defined quasi-momentum eigenstates, plane waves like these two, which are valid single particle, were a valid creation, a canonical creation of annihilation operators, and then you've mapped this Hamiltonian to this Hamiltonian, which is now completely diagonal. It's made up of number operators, and it has the standard cosinusoidal dispersion relation you'd expect for a 1D chain, where you would have some bandwidth of 4t, and you have some Fermi level, and you go between minus pi over a and plus pi over a quasi-momentum. In the limit that m goes to infinity, so you have an infinite system, this would become a continuous dispersion relation. Okay, so that's a very, very trivial example, and you can easily generalize this to 3 dimensions, to a 3-dimensional type binding lattice, appropriately, just by adding, making everything vectorized. Nonetheless, what you end up with is a diagonal one-particle term. And as I said, diagonal one-particle terms just as sums of number operators for each single particle eigenstate. And it means that you can write down the many-body eigenstates for this Hamiltonian really, really easily. They are just the Fock states in the basis defined by the eigenstates. So in this case, I've chosen the alpha to be the eigenbasis now, rather than the K. So going back to using alpha, and that means any state of this form where we put particles in any of the alpha states, because the alpha states are the eigenstates of this Hamiltonian, this will be an eigenstate. It's a many particle eigenstate, and its energy will simply be the sum of all of the single particle energies of all of the states that we've populated with particles. And that just goes back to what we said right at the beginning of the first lecture, where we wrote down what a single particle Hamiltonian looks like. This is what a trivial single particle Hamiltonian looks like. Unsurprisingly, if we can get a Hamiltonian into that form, we can compute absolutely everything from it because it's a non-interacting problem. So let's look at some key properties. What's its ground state? Well, this is really, really, really easy. We've got n particles, we've got a whole bunch of energy levels. What's the lowest possible state that we can have when we have n particles distributed among n levels and we can only put one particle in any one level? Well, we just get a Fermi sea. So we just take the spectrum going up here and we populate each level all the way up to n till we get to the Fermi level. And the ground state will therefore be the occupation of all of the lowest energy eigenstates, the n lowest eigenstates. And it's just a particular Fock state where you bunch up all the particles at the lowest possible single particle energy states. Excited states of the system are then easy. We could just add a particle above the Fermi sea. If we added it right above it, if we put it in the state n+1, that would be the ground state to having n+1 particles. But if we put it in any other state, so there's a gap of unoccupied states, this is clearly an excited state of n+1 particle system. We've added a particle by applying a creation operator. We could also suck a particle out of a particular mode. Now this is not a ground state because we've got a hole in our Fermi sea. Or we could create a particle hole system. So in this case, this was n+1 particles, this is n-1 particles. This is still in the n particle sector. So we take a particle out of here and we put it up here. And that's a particle hole excitation. And this is now an excited state in the n particle sector on top of our Hamiltonian. But it's still an eigenstate, it's just not the ground state anymore. So what about thermal states? Well, a thermal state is by definition given by this thermal operator here. It's a density matrix that describes your system. And it's the Hamiltonian, the exponentiation of the Hamiltonian minus beta. And I've added a chemical potential here so that you can, as a Lagrange multiplier for controlling the particle number. And you might want to work out at some temperature, what's the occupation of a given eigenmode of the system. So a given state alpha p, which is an eigenstate of the system. So the Hamiltonian is diagonal in this basis, and the number operator is given by this. Well, this looks like a pretty messy calculation, and in fact it actually is if you expand it all out. So you need to take a trace of this operator, but we know that there's a basis where this operator is diagonal, so we should clearly work in that basis, which is the Fock basis of the C alphas, which I've written here. And if you do that, you can use the Fock basis and sum over the top and bottom are two separate traces. This is the partition function. This is the thermal average. And you've got to work out these two, the denominator and the numerator. And this simplifies for non-interacting systems, for diagonal Hamiltonians, very nicely, because each mode is made up, so the Hamiltonian is made up of a sum of number operators. And number operators for different modes commute with each other because they're made up of pairs of operators which anti-commute. And if you anti-commute twice, you get a commutation relation. So all of the number operators commute with each other. That means that this operator exponential splits into a product of exponentials over each single particle mode. So that sum becomes a product outside the exponential. And that only happens because the operators that are in the exponential commute with each other. It does not apply if they don't commute in general. So what that means is that we can break up this trace into the product of these terms. And now we only need to concern ourselves in any one of these terms by the number state for the particular mode of interest, the mode that's inside here. And so that's the denominator, and then this is the numerator is a little bit more almost identical. It has all of the modes except the one you're interested in are exactly the same as in the denominator, except the one you're interested in has an additional number operator down here. So that's the thing you need to calculate. So if you do this divided by this, you can see there's a lot of cancellation, and in fact they completely cancel, so that you only need to worry about the particular mode that you've occupied. You need to work out this expectation value down here and this expectation value up here, and that's pretty easy to do. There's a question on the problem sheet to do it, and what do you end up with? You end up with the Fermi-Dirac distribution, which is, you would have predicted that from the offset, but this calculation shows how you do it and why It's simple to do for non-interacting particles because of the fact that all of the parts of the Hamiltonian commute with each other. It makes the calculation extremely trivial. That does not work for interacting systems, unfortunately. Okay, so the moral of the story is we've got a diagonal Hamiltonian, we're in business. We can do everything we want. We can do finite temperature and zero temperature calculations. So here's a nice thing about non-interacting ground states. Okay, so you've got the Fermi sea. So here's a nice 2D system written in, presumably this is a grid in momentum space. We've got our nice Fermi surface. We've completely populated all of the interior of it. And that's our Fock state that describes the ground state with n particles in it. And this is what it would look like arranged in energy if we wanted. Now, we can consider any state like this, any Fock state, effectively, we can consider as a quasi-particle vacuum. So what do I mean by that? I mean that it will basically behave like the vacuum if we introduce a particle-Hole transformation. And that is, a particle-Hole transformation says that if we're up here in the unoccupied place, creating a particle creating a quasi-particle is exactly the same as creating a particle, and annihilating a quasi-particle is exactly the same as annihilating a particle. But down here, inside the Fermi sea, creating a particle is actually the same as annihilating a particle, because you can't create any particles, there's nothing there. So the only way you can create a particle is by removing a particle. So you basically flip the definition of creation annihilation operators inside the Fermi sea, but you leave them identical outside the Fermi sea. And by doing that, you still end up with a new set of operators A that obey all of the standard commutation relations. So they still define a genuine fermionic Fock space. But the trick now is that all of the annihilation operators, that's this and this, when they act on the ground state, the Fermi sea, they all vanish. And that's the definition of a vacuum. A vacuum is any state that makes all annihilation operators vanish. We saw that in the last lecture. But we've basically created a new vacuum now by using the Fermi sea as a vacuum, by redefining our operators through what's called a particle-Hole transformation. All right, so it behaves analogously to vacuum. Why is that useful? Well, it's useful for something called normal ordering. Now, what is normal ordering? It's where you have a bunch of creation annihilation operators, and you want to put all of the creation operators to the left and all of the annihilation operators to the right. Okay, and the reason you want to do that is because you want the annihilation operators to hit the vacuum, and the creation operators to hit the vacuum the other side. You've got the ket of the vacuum. You want annihilation operators, when they hit the vacuum, they disappear. And creation operators, when they hit the bra of the vacuum, they also disappear for the same reason. So if you normally order any string of creation operators, which will be some permutation of them, and you'll need to track the permutations because of anti-commutations, you will, when you put them into normal ordering, the normally ordered operator has a 0 expectation value on the vacuum. So here's an example on the real vacuum. We've got these operators, they're not normally ordered, but we want to normally order them. So all we do is we need to shuffle all of these creation operators over to here, and we get something like this. Now this is normally ordered. We've got all the creation operators on the left and all the annihilation operators on the right. Of course, it's not unique. You could have reordered these operators among themselves and you get rid of this minus sign. It's not unique, but it is unambiguous. Okay, good. So once you've got this, this now disappears if you take an expectation value. So that's what the property is here. Normally ordered operators disappear when you take an expectation value. It kills them. Now, the next interesting property to define is something called the contraction of operators. And this is a rather subtle idea, which I'm going to explain now. And what it means is if I have two operators, the A and B are creation and annihilation operators. Of some, they could be both creation operators, both annihilation operators, or some combination of them. And I'm going to define the contraction of them with these dots here. And that means that I'm going to take the original operator and I'm going to subtract its normally ordered version of it. And it's going to be the difference between them. And there's not actually many options. There are only two options this can give you. It could be that you need to reorder A and B because they're not normally ordered. So for instance, if it was C, C, dagger, that would be in the wrong order. You would normally order them, you'd swap them around, you pick up a minus sign. And that means that the contraction would then, because there's a minus sign there, that would turn into a plus. The contraction would just be the anti-commutator between them. But they're creation and annihilation operators, and the only commutator they have is either 0 or 1. So it's basically a delta, and it depends on what the modes were that you had in A and B. Or it could be that the operators were already normally ordered, in which case the normally ordered version equals the AB, in which case it's 0. So what it's telling you is, it's telling you whatever the value is, a contraction of a pair of creation and annihilation operators is always a C number times the identity operator. And that C number could be 0 or it could be 1. And in fact, the C number is exactly the vacuum expectation value of A and B, which will either be 1 or 0. Now we come on to, we can use this property to something that's a very non-trivial result, which is a bit tricky to prove in general, and I'm not going to do that, and requires a bit of work, but you don't need to know it in general, because actually there's essentially only one version of this theorem you need for what we're going to do. And it's called Wick's theorem, and it's basically a powerful identity for connecting products of creation and annihilation operators to normally ordered products. And it's, as it says here, it's a cornerstone of diagrammatic techniques, which we're not going to introduce or use here, but it's really important. So what we will use is we'll use the version of what happens when you have 4 creation and annihilation operators. So remember, our interaction term in our original Hamiltonian was made up of C dagger, C dagger, C, C for some various single particle modes. So it had 4 operators in it. So what would happen if you wanted to decompose that into a sum of normally ordered bits? Well, Wick's theorem tells you that you can write that as its normally ordered version plus the normally ordered version of A and B with C and D contracted to each other. Remember, the contraction of C and D is just the identity operator times the expectation value of C and D. And likewise for all possible permutations. And you'll get many terms, but the last 3 terms are the most important for us because they are completely contracted terms, which means that they are just vacuum expectation products of 2 vacuum expectation values times the identity. So that's what I show here. If you take the expectation value on the vacuum of this 4 operators, all of these terms vanish because they contain normally ordered operators, which vanish under the vacuum, and only the last 3 terms survive. So basically, you only get the fully contracted identity terms contributing. Another way of writing that is the expectation value of the vacuum for products of creation and annihilation operators factorizes into these products. The vacuum expectation value of AB, the vacuum expectation value of CD, etc., minus these. There's 3 terms. And this is true for any creation and annihilation operators. They don't even have to be, they can be in any basis. Okay, so the vacuum is the vacuum for every creation and annihilation operator. So it didn't matter what basis we used. We could have used the C alpha basis. We could have used the DK basis. We could have used anything we want. It doesn't matter. This applies to all of them. Now, here I'm talking about the real vacuum. But in condensed matter, we don't have the real vacuum. We have some ground state, which involves a Fermi surface. So instead of using the real vacuum, why don't we use the ground state of a non-interacting electronic system? That's exactly the trick we're going to do. We're going to use the quasi-particle vacuum, which is precisely a Fermi surface. And we can define normal ordering with respect to the quasi-particle vacuum, exactly as we did before. And it works exactly the same. First of all, you take a product of operators. Let's imagine that we've occupied C1 dagger, C2 dagger, C3 dagger are all occupied. And then we've got these, remember that if we were occupied, we flip the definition. And if you're in an unoccupied, we leave it the same. So that means that if when we flip to the A, the C becomes an annihilation operator, C2, C1 becomes an annihilation operator, C2 becomes a creation operator, and C4 stays a creation operator because it was above the Fermi surface. And then you normally order this exactly as you would normally. So you put the creation operators here, and then you can re-expand it back out again and you'll end up with, this time, this doesn't look normally ordered now, but it is actually normally ordered. It's normally ordered with respects to the quasi-particle vacuum. And if you took the expectation value of this operator on the quasi-particle vacuum, it would be 0 because it's trying to create a particle in a state that's already occupied. So that's the trick that you use. You have to do a particle hole transformation first, and then normally order with respect to that. So Wick's theorem for a Fermi sea. What about, you could use Wick's theorem using the C operators that we had up here and the A operators that came from them. But what about if we used a completely another single particle basis that's got nothing to do with the one defining the Fermi surface? Because the vacuum Wick's theorem works for all possible single particle bases. Well, it turns out that the Fermi sea quasi-particle vacuum also obeys Wick's theorem for any single particle basis. And the reason for that is you can always write any operator in another basis as a unitary mixture of the C operators, the eigen operators, and then you can convert that each term in that sum to its relevant particle hole transform version, and then you can go and normally order all of them individually. And so basically the net result is that you still have exactly the same result. It doesn't matter any creation or annihilation operators. The contraction of them is the difference between them and their normally ordered version, which is equal to the expectation value of that pair of operators on the quasi-particle vacuum, even though the D operators are not the same operators that define the quasi-particle vacuum itself. It's true for any. And what that tells you is, it tells you that if you've got a Fermi sea or some Slater determinant defining your ground state, or it doesn't even have to be a ground state in principle, some defining your system, the product of 4 creation annihilation operators in any basis can be expressed, the expectation value of that product can be expressed as this combination of 3 terms in any basis. And that is a truly remarkable result that's actually really very useful. And I'm going to show you it's useful by using it to do a variational approach. So we're going to now go back to our interacting Hamiltonian, and we're going to solve it by working out the best possible single particle ground state. So the best possible Slater determinant that describes the ground state of this interacting system, okay? But we're going to use the variational principle to do that. So let me just recap what the variational principle is in case you can't remember from earlier. So this Hamiltonian is not it's not bilinear, so we can diagonalize this bit by doing a single particle transformation. We cannot diagonalize this bit by doing no single particle transformation will ever diagonalize it. So it's too complicated for the process we've been previously describing. But we could use the variational principle, which means if I give you some state, I define what's called an ansatz, a state that's defined by some parameters. And I say, this is my state, and suppose I can calculate the energy of that ansatz. So for instance, if you're solving the hydrogen atom, you might choose a Gaussian wave function, okay? And you can work out what the energy of a Gaussian wave function is for the hydrogen atom, and you would have the width of the Gaussian is your variational parameter, and then you would go and work out its energy, and you know by the variational principle that the energy of that Gaussian wave function for any value of its width will always upper bound the true ground state of the system. So in fact, it will follow some curve as a function of the parameter. It will always be above the true ground state, which you don't know a priori, and you'll then find the minimum energy along that curve, and that is the optimal, at least according to energy. It's the best approximation of Gaussian wave functions to the hydrogen atom that you found, which will have some particular width of the wave function. That's the variational principle in a nutshell for a very simple case. Let me just make an aside here, a footnote almost, and that is actually, if you look at this, if I have 2 different variational wave functions and one gives me a lower energy than another, and they can be completely different wave functions, different types of wave functions, which one is the best approximation? The one that has the lowest energy or something else? Is lower energy always better? Not quite. And there's a really nice example of this in the quantum mechanics book by Messiah on page 768, okay? And he considers the hydrogen atom, and he considers 3 different wave functions, okay? Different ansatz, A, B, and C. A is effectively the exact answer. It's an exponential decay radially for the ground state, which has an S wave, so it has no angular dependence. So A actually is the ground state, contains the ground state if you optimize the value of A. B is some very strange 1 on R squared plus a constant wave function, okay? And C is basically exponential, but it has an R dependence in it. So it's basically, it's like it's got some angular momentum, which it shouldn't do because it's in the ground state. So neither of these are exact, but they have one variational parameter. And it turns out that if you minimize the energy with respect to the Rydberg scale, energy scale, then of course A gives you exactly -1 Rydberg, which is the energy of the hydrogen ground state. B gives you -0.81, so it's above the ground state, but it's not too far. I mean, it's quite far away, but it's not that far. And C gives you the worst. It gives you -0.75. So if we were to look at this alone, we would say, well, clearly this is exact, and this is the next best approximation. But actually, if you look at some physical quantities that you calculate from these wave functions, say, for instance, the average location of the hydrogen electron, which is the average position, because this has got a power law decay, this is in fact radially power law. It's actually got a diverging electron position. The integral for the electron's location is divergent. So it's actually infinite, which is really bad. It's telling you this ansatz is rubbish, telling you anything about where the electron is. This one's not too bad, actually, the C. So what's going on here? Why is this so good in energy, but it's rubbish at everything else? Well, that's because the variational principle only tells you about energy. It doesn't tell you about anything else other than energy. And in fact, if you work out the overlap of this wave function with the exact one, you see that the difference in the overlap, the 1 minus the overlap, you see this one is 0 because it's the ground state, so it's got no error at all. And this one's actually got a 20% error, whereas this one's only got a 5% error. But yet this one has a worse energy. Well, the reason for that is because of the tails of these wave functions, and because B reproduces the behavior better at low values of R, and in hydrogen, the energy of the atom is dominated by what happens close to the origin, because that's where the Coulomb interaction is strongest. But it gets the tail wrong. So B gets the tail badly wrong, but C gets the tail right, gets the tail almost right. It's not completely right, but it's much more realistic. So that basically the point here is having a lower energy doesn't guarantee anything except energy. So if anyone ever tells you that they've got a variational ansatz and that theirs is better than yours because its energy is lower, it's actually complete bullshit. Yeah, you can't trust energy on its own. And that's very true for many body systems. Okay, that was a bit of an aside rant about many conversations I've had with people about variational wave functions. Let's do a variational approach. One variational approach is the Hartree-Fock approach, which is basically we want to find an ansatz that is a single particle, putting a Fermi C, putting particles in orthogonal single particle modes. We don't know what those modes are. We just want to optimize all the single particle orbitals that we're going to put the particles in and find the lowest possible energy in this class of states for the original interacting Hamiltonian. So remember that this is a Slater determinant. So we need to know all these single particle orbitals that we're trying to optimize here. And you can proceed in a first quantized way. And indeed, if you look in some textbooks, they will have the Hartree-Fock written in first quantization. That's fine. We're not going to do it in first quantization. We're going to do it in second quantization. So we won't need to refer to this wave function, to a real space wave function. We're going to keep it all in second quantized notation. Okay, so what do we need to do? Well, as I showed you, for the variational principle, you need to compute the expectation value of the energy. So you need to work out this, which means you need to work out this expectation value. And look what we've got. We've got this expectation value, which is a single particle operator. But the problem is we've got this one. And this one is tricky because it's biquadratic. But we can decompose this using Wick's theorem. And that's the beauty of Wick's theorem. So we don't know what this Slater determinant is, psi. Okay, it is a Slater determinant. And all we know is that we could define, according to that unknown quasi-particle vacuum defined by that Slater determinant that I don't know, I can use Wick's theorem with respect to it. And that means any operators, the C ones in particular, I can decompose their products with respect to this unknown Slater determinant. And that's great because it means I can do this, which is this line here. And actually it simplifies even more because I know that this has exactly n particles in it. So this expectation value and this one must vanish because this particular product ordering of the products of operators is creates 2 particles on top of this. So this is an n plus 2 particle state having an expectation value with an n particle state. And that's 0 because they're in different particle number sectors. So this disappears. This wouldn't disappear if, for instance, we were doing BCS theory where we violate particle number conservation. We have superpositions between different particle number sectors. Then these anomalous terms can be retained. Okay, so we're going to have to calculate this expectation value here. And you'll notice that if you insert this into here, the thing that appears all the time is an expectation value that looks like this: C dagger, some mode, C, another mode. So let's call that rho alpha beta, because in fact, what it's actually called, this is called the single particle reduced density matrix of the system. So for fermions, there is one slight technicality that you write the indices of this matrix in the inversion of how the operators appear inside here. It's not essential, but it just makes some of the mathematics a little bit simpler if you do that. So this is called the single particle density matrix, and its properties are really important for what we're going to do. And you can see that the expectation value up here will depend entirely on this rho quantity. In fact, I've written it out here. This is what you get when you insert. So these are the 2 terms that came from Wick's theorem, and this is just the term on the single particle term. So we need to minimize this energy with respect to the matrix elements of rho alpha beta, but they must be constrained that those matrix elements, rho alpha beta, were derived from a Slater determinant, okay? Because this single particle density matrix, this is the definition of a single particle density matrix for any state, not a Slater determinant. This didn't have to be a Slater determinant for this to be a density matrix. But there's a very special form that single particle density matrices have for Slater determinants. Because in general, for any state, this single particle density matrix is a Hermitian matrix, and in fact, it's a positive semi-definite. So it has non-negative eigenvalues, and it's Hermitian. And its trace is the number of particles in the system. So if you sum the diagonal elements, you get the total, because the diagonal elements are just the densities in each of the single particle modes. If you sum them, you get the total number of particles. That's true in general, but there's one additional property that only applies to Slater determinants. And that is that if you have a Slater determinant, the single particle density matrix is what's called idempotent. It's a projector. What it actually means is it's a projector onto the occupied space of single particle modes, the Fermi sea. Okay, and the way to see that is work in the basis, the basis that defined the original Slater determinant. And if you work in that basis, the diagonal basis, what you find is that the density matrix is diagonal in the basis that created the Slater determinant, and it has an occupation numbers along the diagonal that are all 1, 1, 1, 1, 1, 1 for the occupied modes and 0, 0, 0 for all the unoccupied modes. Okay, so it looks like this, basically. It's just a projector onto the occupied subspace of single particle states. And because this is true in one basis, it's true in any basis. It won't have this form, it won't be diagonal, but it will obey this property, because this property is true for this matrix. It must be true for the matrix written in any basis. If you unitarily rotate it, it doesn't change this, this property. So what we get that rho squared equaling rho is both a necessary and sufficient condition for the state that generated it to be a Slater determinant. The sufficient bit comes from the fact that if you diagonalize rho, you will get a bunch of eigenvalues that are unity, and then you simply use the eigenmodes for those eigenvalues that are unit valued to create a Slater determinant. So you can go both ways. So it's necessary and sufficient. And that's really powerful because it means that we can constrain when our density operator is a Slater determinant by simply enforcing that it must be a projector. Good. So what are we going to do? We want to minimize the expectation value of the Hamiltonian. The full interacting Hamiltonian over Slater determinants is equivalent to minimizing the functional with respects to the single particle density matrix, such that the single particle density matrix obeys rho squared equals rho. That means we can rewrite this as a variational equation, and we introduce a Lagrange multiplier. So we call this, that's capital lambda. It's a matrix of Lagrange multipliers whose purpose is to enforce this constraint. So we're going to minimize this with respects to these matrix elements under the constraint that the equation must obey rho squared equals rho. And we're trying to make this 0. Okay, so we're trying to find a stationary point, which we hope is the minimum of the function. And this is Hartree-Fock. So what we do is we take the derivatives. Well, the derivatives of the energy function with respect to rho, we're going to call that a single particle matrix, little h. In fact, it's called the Hartree-Fock Hamiltonian, effective Hamiltonian, and it's basically the normal single particle Hamiltonian plus something that involves the interaction, but these are the interaction matrix elements multiplied by the density, by the one particle density operator. So this is in fact a single particle Hamiltonian, an effective single particle Hamiltonian that includes the effects of interaction caused by the mean occupations of the states of the system. So it's a mean field. This is the mean field term that's coming from the interaction being treated in this way, in this approximation. Notice that this functional H, this matrix H, depends on rho. So that means that it's a function of rho itself, and that makes the problem a little bit non-trivial. It means it's a nonlinear optimization problem. So if we go and work this out, what do we get? Well, the first term gives us this, and the derivative of this second term gives us these terms here, where you're differentiating rho, rho squared, and rho. So you end up with these terms here. And this must equal 0. And this equation looks a bit tricky, but actually it's not so bad if you write it as a matrix equation, because this is, you can just think of this as a matrix equation, with respects to the mu and nu indices here. And as a matrix equation, it's equal to this. And how does this matrix equation, how can we guarantee this matrix equation is always satisfied? Well, it turns out that that's not too difficult. If we multiply both sides of it on the right and left by rho, and use the fact that rho, if we multiply on rho on this side, rho on that side, rho there, rho squared is equal to rho, remember, that was a fundamental definition. The equation simplifies to this, which is actually just the same as saying that this is true. So what it said is that in order to minimize this functional, we need to find a single particle density matrix, which is rho squared equals rho, which commutes with the effective Hamiltonian H. Now that sounds like it's easy, should be easy to do. Okay, so the Hartree-Fock equation, that's what this equation is the Hartree-Fock equation, states that the density matrix, which makes the energy function stationary, commutes with the Hartree-Fock Hamiltonian. But this is harder than it sounds because this depends on rho, so it's a nonlinear problem. So how do you solve a nonlinear problem? Well, it's quite difficult to solve in general, but one way to solve it is to use an iterative loop and do a constant reinsertion. So that is, you build a Slater determinant with some single particle modes. You know, just guess them. They could be the eigenstates of the non-interacting part of the Hamiltonian. That would be the most obvious guess to use. Then you work out a single particle density matrix. You work out the effective Hartree-Fock Hamiltonian. you diagonalize the Hartree-Fock Hamiltonian that came from the density matrix you originally assumed from this state. You get a whole bunch of new eigenmodes of this Hamiltonian, and so you then build a Slater determinant out of those eigenmodes, which will commute, have a density operator that commutes with the effective Hamiltonian you just generated from it. But you'll have to then recompute the effective Hamiltonian by recomputing the density matrix of your new state, which then recomputes a new effective Hamiltonian, which may not now commute with the original state. So you then rediagonalize it, reinsert it, and go round and round this loop until the two, this and this, commute with each other. That's the trick. So you basically do it, repeat until convergence. It's not guaranteed to converge, but it almost always does for most simple cases. And at the end, you'll have variationally optimized the Slater determinant that gives you the best Slater determinant approximation to the ground state. Okay, so that's what Hartree-Fock looks like in second quantization. It all relies on the one particle density matrix of the problem, because Slater determinants are fully defined by the one particle density matrix because they're such simple states. Okay, I'm not going to finish this section today. I'll just get started on it. I just want to introduce a BCS Hamiltonian, and this is something you would have encountered in a previous lecture. And I just want to start reformulating it in a way that's going to allow us to do mean field on this Hamiltonian. But I'm not going to finish that in 10 minutes, so I'm not going to rush it since we've got time next week. So I'll just lay out some of the foundations, and then we'll call it a day for today because we've done quite a lot. Okay, so let's have a look at what we mean by the BCS Hamiltonian. The BCS Hamiltonian, now I'm imagining I've got a 3D crystal with electrons in some three-dimensional dispersion relation. I'm using a vector K to determine the vector, and I've got spin. So I've made the problem. This is now the kind of problem that you would see in your research papers. And I'm going to add the BCS effective pairing term. So there's already been a whole bunch of approximations of phonon modes introducing a retarded potential, blah, 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 that you boil down to get to this point here. Okay, so this is already a toy model that we're using. And the toy model is that we introduce a constant pairing interaction. It's got a negative sign there, but it only acts on a very thin shell around the Fermi surface, a shell that will have a width that's given by, in fact, the Debye frequency divided by the Fermi velocity. But it's just got some finite width. And this dash on the sum here is saying I'm going to sum over all of the quasi-momentum states inside this little shell around the Fermi surface. Okay? And what this interaction does is it takes a pair of up and down electrons at plus and minus. So they're, in fact, they're time reversal symmetric pairs of electrons, of an up and down electron at opposite sides of the Fermi surface with opposite spin, and it's going to scatter them into another pair of opposite momenta with opposite spin, with Q. So it annihilates the Q and scatters it into the K. That's what this pairing term does. Okay, it's a two-particle scattering term, but it describes a attraction because it's got a negative sign here. So that's the basic physics of the problem. It's essentially the problem that Bardeen, Cooper, and Sharif boiled superconductivity down to, and then they wanted to solve this problem. But of course, this is still an interaction term, so we can't diagonalize the Hamiltonian exactly. But what we can do is we can use a variational approach using the kinds of methods that we've been discussing. Except the difference is now that we're going to use a variational approach that doesn't conserve the number of particles. So we're not going to use Hartree-Fock, which would have a fixed n particle state. We're going to create an ansatz that will have superpositions of different particle numbers. We're going to violate particle number super selection, but we're going to do that because it's going to give us a really easy way of getting an ansatz that describes the system and describe its energy. So, and we know that the error we make by using the superposition has a particle number fluctuation that scales as 1 over the square root of n, is what we're going to find. So as we go to the thermodynamic limits, we'll end up with effectively the same answer we would have got had we used fixed n to begin with. Okay, so let me just do a little bit of the background. We need to rewrite this Hamiltonian in a way that's going to make sense and allow us to diagonalize some mean field Hamiltonian. And the trick here is to take this pairing term here and rewrite it as some scalar bk, which is the expectation value of this operator. Notice it's an expectation value of C dagger C, of C dagger C dagger. So this is one of those anomalous terms that I got rid of earlier because it contains two creation operators. So clearly, whatever state I'm taking the expectation value here cannot be a number state because it would be 0, and then we would have nothing. And we're going to basically divide this interaction up into two parts, into the pairing parts. And what's left here is the actual operator itself minus its average value. So whatever this thing is, this is an operator that's called the fluctuation. It's the bit of the operator that it goes beyond its mean value in the unknown ground state that we're trying to find. Okay, and this is the expectation value of this operator in the unknown ground state that we're trying to find. And if we insert this expansion, which is by no means a trivial thing to do, into the original Hamiltonian up here, and we ignore any term that involves the fluctuation squared. Okay, so we insert this, but we get rid of anything that involves the fluctuation squared. So we only retain terms that are linear in the fluctuation, which means we'll end up with this squared, we'll end up with this, the linear terms, and then we get rid of the quadratic terms. And this gives us a Hamiltonian that looks like this. So these are the scalar terms, and these are the two linear terms, and we've got rid of the additional fluctuation squared term. Now, by doing this, we have effectively made the Hamiltonian, it's no longer by quadratic, it's now just quadratic. It's not bilinear though. Bilinear would be this, okay, where we would have one creation operator and one annihilation operator. We don't have that. We now have two creation operators and two annihilation operators here, which is anomalous. And that comes back to this value being 0. And what we want to do is we want to diagonalize this Hamiltonian, because now we can diagonalize it with a single particle transformation, but it has to mix creation and annihilation operators up. That's the moral of the story. So we can rewrite that as this. So we can add a chemical potential we can add the chemical potential into our problem, because now we don't have a fixed number of particles. We should introduce a chemical potential to control the number of particles we have in our system. And we bury that inside the dispersion here by just rewriting it as a zeta. And we need to diagonalize this. And it doesn't conserve particle number. And as I said, we're going to introduce this. And we're going to bundle up the sum over G and K of these BK terms. So these are all the expectation values of these pair operators. So we're going to sum them all up, and we're going to call the sum of them delta. And that is what's called our order parameter. And if we do that, we will arrive at the following problem, which I'm going to end here, and we're going to talk about this more next week, is that I want to now, I've got this problem now, which looks relatively straightforward. It's a quadratic problem, and I want to diagonalize it. So I want to put it into a form that only has C dagger or some number operator of some modes. And what they will turn out to be, they'll turn out to be the Boguslavov quasi-particle modes of our system. So we want to diagonalize this Hamiltonian, and we can do that using second quantization and matrix and a few simple matrix manipulations, which you can already see down here. And that's what we're going to do next week to finish this off. And we will find the BCS solution to superconductivity will pop out as a variational method of solving this Hamiltonian. But I'm going to finish that next week, and then we will also then move on to looking at linear response. So if I go back, next week we'll finish the little bit of this, and we will go on to looking at Green's functions, formalism, and the describing linear response. And I might get that finished next week, and maybe a little bit of this I might just start talking a little bit about Fermi liquids. And then in the following week, we'll finish these two here with the time we've got. Okay, thanks for your attention, and I will see you next week, 9:30.